Alright, hey everybody. I'm going to start the YouTube video on the integral of from negative infinity to infinity of e to the negative x squared dx. But I'll need to cover some background topics before this. So let's begin. In calculus, we talk about how if we have the integral of a function, let's say f of x, we will produce another function, capital F of x, and this is called the antiderivative. However, in some cases, we cannot integrate the function. Let me expand on that. In the case of normal functions, let's say we have cosine of x dx. The result is sine of x plus c. This is known as an elementary antiderivative. Now, what an elementary antiderivative means is this can be expressed in terms of the polynomial, trigonometric, and logarithm functions that we do know of. But in this case, let's say, I'll give two examples here. In this case, e to the negative x squared dx, it will produce a function. But this function cannot be represented in terms of the functions that we know of. So I'll just leave it as a question mark. Another common one is the integral of sine of t over t. This one is also another one where it's a non-elementary antiderivative. So there's really no answer that we know of like this. So when you see this, you're going to think, okay, well, if this doesn't have an elementary antiderivative, how do we even solve this in the first place? Well, we can still solve this, but we'll have to solve it a little different. In calculus 1b, to find the area underneath a function, what you do is you take the integral of a function, let's say f of x, from a to b, and then you find the antiderivative, which is capital F, and you plug in b in place of x, and you plug in a in place of a. X in place of a. However, in this case, we don't know what capital F is. We can't write it out that easily. So we can't use this method to solve for this. So for this, we'll actually need to use a different method. I'm going to derive the expression on how to do this once, and then I'm going to redo it a second time, but explain in much more detail. So here's the beautiful integral again here. And we know for a fact that this integral doesn't diverge. It won't go to infinity. It'll actually give us a finite number. I'm going to call this I. Now, this is our integral, and this is our value. I'm going to do something a little different. What I'm going to do is I'm also going to say, I'm going to take the integral of the same function, e to the negative square of something. But now, instead of x, I'm going to replace it with y. what I'm doing here is this integral, this is still the same function. It still produces the same value. I just switched the variable name from x to y. And I'm going to continue deriving this expression on how to actually get the value of this. Now, this is the way that you might do it on a test, because you don't want to spend too much time explaining every step. So what I'm going to do is I'm going to say this is I squared, and I'm going to multiply them together. And now, this, the value, because this is I and this is I, the final value is I squared. Next, what I'm going to do is I'm going to move in the function together. Now, why is this possible? This is impossible in a lot of cases, but here, x and y are actually independent of each other. They're on an orthogonal axis, so this is actually a square domain. So we can use Fubini's theorem. And because x, the function x and y, they're actually separable in terms of the exponential functions. I'm actually going to talk more about Fubini's theorem after I finish this derivation, but we'll talk more about the y later on. Now, I'm going to combine them together to write it as e to the negative x squared plus y squared dx dy. What I'm going to do next is convert it to polar coordinates. So, I'm going to let r squared equals to x squared plus y squared. And I'm going to let theta go from 0 to 2 pi. So what's actually going on is pretend that this is the xy axis that you're integrating on. And I'm going to let r be whatever point that we are on the coordinate system. And we're going to let theta go from 0 to 2 pi. So theta is going to start here, and theta is going to end here. So it's kind of sweeping out a disk in the coordinate system. And now what I'm going to do here is that because we're working with x and y from negative infinity, which can be here, 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 or here, and we're converting it to polar, we're going to let the circle expand. The radius expand outward to infinity. So for our innermost integral, this will be infinity. And theta, since we want to cover all 4 quadrants of the coordinate system, we're going to let us go from 0 to 2 pi. And this becomes 2r squared. So now we have negative e to the negative r squared r dr d theta. What we're going to do now is this depends on r only. So I'm going to move the integral out. Let me erase some of the stuff above. This integral evaluates to 2 pi. And now we'll begin solving this. So let me first solve the regular integral. This can be solved using a u substitution. So we let u is equal to minus r squared, du is equal to minus 2r dr. This becomes e to the negative u du. And the resulting integral is minus 1/2 e to the negative u e to the positive u plus c. And plugging the variable r back in, we get this answer. We get this answer. So we're going to substitute this answer back into our expression below, and we're going to take the limit. Now the c constants cancel out here, and what we're left with is actually 2 pi. The limit of negative 1/2 e to the negative a squared actually goes to 0. This can be shown using L'Hopital's rule, but I'm not going to do the whole proof here for time's sake. So this will get to 0 times 0 plus 1/2 times e to the 0 power is 1. So our final answer is 2 pi times 1/2 is equal to pi. Okay, so this is our golden answer right here. So now, after all this work, we know that the integral of this is equal to pi. So that means if this is pi, if I squared is equal to pi, I is equal to square root of pi. Okay, so this is our answer. But why? What are we doing behind all of this crazy work right here? Well, we actually have to talk about Fubini's theorem and coordinate transformations first. Let me just erase all of this. So this is Fubini's theorem. If a function f is continuous on the rectangular domain, then when you take a double integral over an area of function of f of x and y, you actually can switch the order of the integrands. So this is part one. This is Fubini's theorem. And there's actually another part that's going to be important. If the function is separable, we can actually pull out the integrands entirely. This trick will make our computation a whole lot easier. Now, let me clarify what I mean by separable here. Separable is whenever we have a function of both x and y, that we can separate into a product of just a function of x and just a function of y. So for instance, f of xy is equal to e to the negative x squared plus y squared is equal to e to the negative x squared times e to the negative y squared, which would be your g of x here, and e to the negative y squared would be your h of y. And also, let me clarify what I mean by a rectangular domain. So, for rectangular domain, this would be the region that you're integrating over. And as you can see, this is a rectangle. Now, in linear algebra, after you finish Math 1D in linear algebra, you're going to learn about the concept of bases in coordinate systems. In this case, the coordinate axis x, which is the basis x, and the coordinate axis y, these two are orthogonal. They're 90 degrees to each other. So, x and y here are totally independent of each other when you're doing a double integral. And this is how Fubini's theorem can apply here. We can split double integrals apart, and we can rearrange the order of double integrals because this is a rectangular domain. Let me give you one example where it doesn't work. Now, for this is not a rectangular domain. What this means is Fubini's theorem can't apply here. If you look at the basis vectors or the coordinate axis x and y, they're not orthogonal. The angle here is not 90 degrees. And so, some value of y will actually fall onto the axis of x from our perspective. And so in this case, Fubini's theorem doesn't apply. But for the purposes of Math 1D, we don't have to worry about these crazy coordinate systems. This is what we're going to be working with. Since I already talked about Fubini's theorem, I can go into more depth on the why and the how behind the method that we use to solve the e to the negative x squared integral. So in this case, this is the graph of e to the negative x squared. This is actually known as the probability distribution integral. And if you're doing stats, or if you're doing physics, including the complex wave function, you might see this graph appear again. And so in this case, we'll view minus a and a as sliding bars. So we're sliding minus a toward negative infinity and a toward positive infinity. Now let's talk about the function f of x, y. This is our x-axis. This is our y-axis. This is the y-axis in the negative direction, and this is the x-axis in the negative direction. So, this is a, this is minus a, this is a, and this is minus a. And this is 1, right here. Now, when you graph this function, it's very similar to this. This is basically a 3D version of this 2D graph. And here, let me trace out the domain. Our domain here is a rectangular domain. So this is our domain right here. So if this is our domain, let me graph it right here. We're actually going to integrate within this domain. And in this case, both the a's on both the x-axis and the y-axis are going to be pulled toward infinity and negative infinity. So this is of length a right here. This is of length a right here. This is of length a right here. And this is also of length a right here. So this integral can be interpreted as the area of this function, or in this case, the 2D function f of xy from minus a to a, from minus a to a along the x-axis. Let me kind of fill it in with some color here. So we can kind of view this integral as the area along the x-axis, ignoring the y here. And similarly, for this integral, this can be interpreted as the area So the integral of y can be interpreted as the area underneath along the y-axis, ignoring the x part. Now, you're probably thinking, okay here, how does area times area equal to volume? Well, in this case, we're actually not considering any units. We're just working with this numerically. And so the answer we get by multiplying these two together is actually the area underneath the total function. But this somehow intuitively makes sense. because we're actually going to rely on this fact that these two integrals actually are the same value and also in a rectangular domain to allow us to use Fubini's theorem so we can solve the answer. So, just a quick refresher. We use the fact of Fubini's theorem